Today I'm going to do something that I've seen happen in a few interviews that I've had over the last couple of years. I think this is gaining more popularity among the interview circuit. The situation is you have an interviewer who is maybe a little bit unprepared. Maybe they honestly do not care if you get hired or not. They're not looking to help you. They're just trying to get their interview done and move on. So like, okay, let's see what they can do. And they flip you this, which is, they give you some coding problem and no infrastructure, and they want it to run, and they want you to do all the template code yourself. And oh, by the way, it has to be in C++, and good luck. And the problem that I've seen come up actually multiple times in the last few years, more than once, is merge K sorted lists. They just tell you the algorithm. If you need a description, they'll give it to you. But if you haven't seen it before, you're not going to get it. You're just not. And the main reason for that is because it requires pretty good working proficiency, not just knowledge of, but proficiency in the standard library for several data structures that are pretty gnarly to run at all. And they say, okay, you can use whatever data structures you want, you get to choose. And that particularly comes into play for the format of the input lists. So let me just go ahead and start writing out some template code, because really you're not going to have time to plan out the algorithm. If you don't just know it, you're not going to have time. And they give you a blank slate. So here I'll start with what I've got. I've got an empty main.cpp, and I've got a CMake list file, because like as much as they have me make the code from scratch, I've never had to make a CMake lists file from scratch or anything, or never had to come up with compiler flags or any sort of that stuff. So this is something I've not had to do in an interview. So this is why I've set it up before the video. What we've got is just standard set it up. Realistically, I think this defaults to GCC, which does not have pretty much the most important feature of C++ 2023 implemented, which is the standard libraries modules. It doesn't have that, and I'd be surprised if your interviewers are ever seen that before. But in my particular environment, it doesn't even support that anyway. So I'm mainly going to be using features from C++ 2017, I think, at the latest. Anyway, so setting up the version and then telling it to compile and run, and then that's it. So with that in mind, let's go ahead and one thing I didn't do is make a lesser folder where all the generated files will be. So let's go ahead and change into that, and then we'll start with our code. All right, so first we need is a main function, because this is C++. It's main. I'm probably not going to pass any arguments, but realistically, this is probably the most flexible signature you can use, argc. So a number of arguments to come in, and character pointers, so char. This is a standard C++ main file, or main function. And what it does is number of arguments from standard input come here, and then the whatever your string thing inputs are, I think it automatically separates it by space. So if you pass arguments through standard in, that's a Linux stream. That's how you pass arguments to functions on Linux, and commonly so in Windows, but definitely on Linux. That's how you get those inputs. But I'm not going to use those necessarily. All right, what do we need? This is a merge K algorithm. That's it. They didn't even give me a written description. They just named it, and then that's it. So we get nothing here. What we're going to do is make the function signature. First question is, what's it going to return? Merge K sorted lists is going to take as an input multiple lists. Now on LeetCode, those are in the format of linked lists. But when you're given no infrastructure, linked lists are a pain in the rear to initialize. So you need something that's syntactically fast. You could go with vectors, which is the standard go-to if you need a dynamically allocated array with, meaning the size can vary. Usually you'd go with vectors, but those have a problem. And you're not going to notice this unless you know the algorithm itself. The K sorted lists are going to act as you're basically funneling multiple things into one thing. You have multiple streams coming in, and you know that they're sorted, so you don't have to reorder them or anything, but you're basically taking the front part of each and putting them in. So this is going to be like a forward moving queue, meaning that would be why a linked list would be fine, because you could just, push that forward like a queue. You can continually like pop things off the front of each of the lists and then bring in the next head into your realistically, I should just describe it. I don't think you'd have necessarily time to describe it in an interview unless you're really good at the syntax. But what it is you use a priority queue. So the data structures are, I'll write the comments down here. Approach. You're going to use a priority queue on the heads of the lists or the fronts, meaning only the heads will be in the list at a time. And you're going to continually pop the whatever the smallest thing is off of the list at a time. And then every time you pop something off, you put, you increment that list, and you put its next head on. And that way you've always got this multi-way comparison going at a time. And then you're continually spitting out the sausage that is your output list. And that could be whatever format you want. A vector is fine. Personally, I use double-ended queues all around. A regular queue, I think, is too restrictive of a data structure. You can't really access the intermediate parts, and a double-ended queue does all the same things, and it's actually lower level than a regular, like, quote-unquote queue object. And yeah, that's pretty much it. So double-ended queue and priority queue. Those are the two big data structures that you need. And then the runtime for that. So priority queues are, so we're building our target runtime at this point. Priority queue operations are log on the input side, so whatever's the size of the queue. So if you've got k lists, then each operation on the priority queue is log k time. K per operation. And then for each of those, you have to do that n times. So n operations, meaning you've got your total input, the length of all the input lists lined up back to back. That's n. You have to do n of these log k operations. So total is n log k. That's your runtime. And then space is realistically it's O of n, because suppose all of your lists are of length 1 and you have to put all of them on the priority queue at the same time. That's O of n. That's worst case. That's why. All right, let's make some more template code. So the function signature is gonna return some list. And that list is gonna be a double-ended queue. So include double-ended queue. You have to know the headers too. And then for the sake of conciseness, I'm gonna use this using keyword. And in this case, I'm also all right with using autocomplete, because in all the situations where I've had to do something like this, I had an IDE where it had at least basic autocomplete, nothing super crazy, but anything that was at least visible on the screen, I had autocomplete available. Or maybe it already had this done under the hood in the environment that was calling the file that I was working in. So this has always been an option. And it saves you from having to write that std : a bunch of times. So it saves that would appear in a lot of places. So this would make it more readable, shorter. Maybe you wouldn't do it in a production environment, but for the sake of an interview, it saves you that little bit. All right, so using this std and then double-ended queue. That's how you spell it. And it's going to be integers. Because they say, oh, you get to choose the data type, whatever you want. So just do integers. They're the easiest. Merge k sorted. And it's going to take k sorted list. So you're going to have I'm just using double-ended queues all around, so I can have the same data structure. Double-ended queue of double-ended queues. And then you can talk about if you should pass it by reference or not. Realistically, you are going to need to modify the input. That is by far the easiest way. So if you pass it just by value, then it's safer. But I would be touching the input in this case because it's already in place. So otherwise, you're just going to have to make a copy if you are passing it by reference. All right. What do we have here? Our approach, we need a priority queue, and we need a loop on that queue, and we need to initialize the queue. And let's see. What we put into the queue, whenever we pop something off of it, we need to keep track of which of these lists that item came from. Now, in the LeetCode linked list implementation, each item has a reference. It's like you're putting quote nodes on the queue, and those have a reference to where they came from already. It's themselves. They have an X pointer. You just get the next thing from the next pointer, and you put that on your queue. So that happens already on its own at the cost of having to put the nodes themselves on the queue. In this case, if it's integer inputs, you still need to track where they came from. The way that I'm going to do that is with a pair. So C++ pair type. So think one of these. Include pair. Is there a header for it? Or maybe it's just, I don't know if it's available on its own. It might be. Let's find out. But in order to compare a pair type, the priority queue doesn't have a built-in way to do that. So you need a custom comparison function. And the way that I'm going to do that is with a lambda. The way that you make a lambda is it's got some gnarly actual type. So just use auto. And it has a couple of parts to it. Oh, first let's give it a name. And then the way you declare it is first some square brackets. This determines things from the surrounding function that you want to be available inside the lambda. Some things are allowed, some things aren't. I don't need any for this particular case. So, and then you have the actual, regular parentheses with the input declarations, and that's going to be 2 pairs. So pairs of integers, A, and another pair, int B. So comparison function. And what it's going to do is return just a Boolean. I think it's, if you want something to sort in increasing order, normally you would use something like this. But since this is a pair and that's not necessarily something that's defined, so that would be greater, and that would be how you do increasing order. So if it returns true, then you get the first thing. That's the first thing that's going to bubble up to the front of the priority queue. If it returns false, then the second thing is going to bubble up to the front of the priority queue. So if you want to go in increasing order, then you'd want to return, let's see. Increasing order, you want the smallest thing. So if you return true, then you want, really? Am I getting that backwards? I could be getting that backwards. Anyway, I was allowed to test on these particular ones. Honest to goodness, was able to write test cases and then hit run and then see how it comes out, and then I'll adjust based on that. So I'm going to do that for this video as well. So return a dot, let's say first, I guess. No, I'm gonna do second for the value, and that'll be a little more obvious later on. Is greater than equal to, or it could just be greater. Doesn't really matter in this particular case. Anyway, the second item I'm going to have hold the value, and then the first item I'm going to have hold the index. All right, comparison function defined. Now let's declare the actual priority queue. Priority. Oh, that's in the header. That's in the header of queue. So second header there. GY. Priority queue. First item is going to be the not atomic, but the lowest level data type. So or it's going to be a pair. Sorry, pair of integers. And then the containing type, usually a vector. In this case, I'm going to do a double-ended queue. It doesn't super matter as long as it's contiguous memory, I guess is fine. I've never actually used one with non-contiguous memory. I wonder if that's common. Anyway, double-ended queue of pairs. And the last one is going to be the type of our comparison function. And to make that easy, I'm going to use declare type keyword and pass in just the name. And that's the signature of it. Now we need to initialize. And this is going to be, so I'm just going to call it Q for Q. And what happens? Let's see. So we want to first give it the first argument is going to be the comparator. That's the for this particular signature. The second argument would be initial values. We don't want to put in the whole, like all of the lists, because we don't have a constructor for putting in a list of lists. We're only expecting it to have just a bunch of pairs added in. So we need to do a loop to initialize it. For, all right, in this case, we need indices as well. So int I equals 0 through I is in the length of the lists. All right, we have our loop structure, and what we're going to do is add the pairs to the list. So q dot int, is it push? Push is the keyword. Push, and then the trick that will save you a ton of time is to be very liberal with the use of curly braces. Curly braces are wonderful, especially in modern C++. They can translate by the compiler to a lot of things. So in this case, curly braces with two things in it will translate into a pair. And same thing when you return, if you return a bundle of things in curly braces, it'll be translated into what the signature dictates, which would be a double-ended queue. So in this case, if we put two things in the list, I, the index, and then the value, so it would be lists I, and then the head of that list, that would get turned into a pair and pushed onto our queue. Now, got to think about edge cases. What if, so we're accessing index 0, what if that list is empty? We got to check for that. If lists I, so if the I item is not empty, and that's a positive return, so not empty, exclamation point. If that particular list is not empty, we'll put its first thing onto the queue along with the index. So that's our initialization. We've got the queue set up. Now we have to do the big loop that does all this initialized stuff and uses it to actually do the sorting itself. So we need a return type. So a double-ended queue of integers. Gonna start with nothing in it at first. So it's going to be a loop. So while the queue is not empty. While the queue is not empty. And it'll be empty when we run out of things. So first we need to get the first thing off the queue, add it to our output, and then add things back into the queue if that particular list is not empty. And here's another reason why C++ 2017 is very much worth learning. I don't remember, did they add this in? I'm going to use something called structured binding, which, if you're familiar with Python, is when you have two outputs for a single input and it splits the components and you have really nice named variables. And the way you do that in C++ is auto. I think auto is required in this case. So auto, and then I'm going to say I and val or something equals q dot top. queue top. And then pop the thing off the queue because I don't need it anymore. Queue dot pop. So we've got, yeah, this is exactly what it looks like. The top is a pair. It's got two things in it. And we're retrieving those items as two separately usable variables instead of having to do what we're doing here with like second and first and whatever those identifiers are. Two things. First is to add it to our output. So ret push back val. Added to our output. Now we need to increment this list, and then if it's not empty, we'll put it back on the queue. So okay, already, let's see, we took the first thing off the queue, but we need to increment the list itself. So lists I dot pop front. And this is the reason we're using a double-ended queue, because I have this pop front function, which with a linked list, you'd like follow the next pointer, get the next thing from the next pointer, and then put that on the queue. In this case, we're incrementing this list and getting the thing from the front of it. So if list, if it's not empty, I is not empty, then we're going to put it on the queue. Queue dot push. Again with the curly braces, we're going to keep the same index because it's the same item in this like overall outer list. I and the thing from the front of the queue. So we could let's say val. Is this? So this is by copy. I guess I'll find out if I can change this. So val is equal to lists I0. I'm just reusing that variable there. A little more readable, push those things onto the queue if the list is not empty. And let's see, is there anything missing? Return statement. Return the thing that we have named as the return. Is that it? Okay. Looks pretty good. So we've got the comparison. We've got the initialization that does one item for each element in the outer list of lists. Push non-empty things onto the list, save their index. We've got our double-ended queue output declaration. We've got while this priority queue is not empty. We've got this taking things off the front of the priority queue. We've got popping things off the front of the off the priority queue, and then we've got incrementing that source list and then adding things back if they're not empty. And I think that's the whole algorithm. All right, so if you're not familiar with priority queues in general, as a bit of background, since you've listened this long, what they do is you'll always have the most sorted thing. So in this case, because of our comparison declaration, the smallest thing will always be the front of the queue, but you have no guarantees about whatever the rest of the queue is. Hence why operations are logarithmic, because if they were already pre-sorted, you could do it in constant time instead. So it's a little bit slower per operation. It's basically lazy sorting. If you put everything into a priority queue and then you all at once, it takes linear time to initialize, and then you pop things off, and that takes log of n time per pop operation, and you have to do n of them, so you end up with n log n total time, which is the same as if you had just sorted it in the first place. So that's priority queues. All right, so now we need test code. In that case, let's make a test case. So void case 1, and no inputs, whatever. Let's declare lists. So a double-ended queue of double-ended queues of integers. And here's where we're really going to abuse this curly braces notation. So we have a list of lists. So we have this outer item, and each thing, so they're going to be comma separated, and each thing in it will get translated into the inner queues. So we can just use more curly braces. In this case, they should be sorted as an input. So what I'm going to do is, so I can be kind of lazy about what the order is. I don't have to manually sort them. I'm going to sort them below. So sort, or it's going to be, let's do a for each. So for each, I'm just going to do this. Auto list in lists. We're going to sort it. And the reason I'm sorting it here is so I can quickly change the sorting order. And the way that you would do that, okay, so we've got beginning iterator, ending iterator. Why is this giving me sorted is undefined? Do I have to include something? Is it? I think it might be this one. Yeah, that was it. So this algorithm header has the sort function included. Right. It's generally safe to assume sorting is n log n time, but this is for test code, so that doesn't really matter. That's not part of the main algorithm. This is just implementing test cases. But okay, if it'll sort it in one order if you do this, and then an easy, quick way to change the sorting order if you want to play around with this, the inside order of the inputs, and then you can adjust this to make sure you get it right. Because your output's going to look like garbage if you get the two clashing. So if this is the wrong direction for the what order the inputs are sorted in, whether it's increasing or decreasing, that's how you'd play with that. So we'd sort the lists, but the outer lists themselves are not necessarily sorted. So let's make some inputs. Let's do I don't know, just some face roll numbers. And then, okay, so we've got our input defined, we sort them, and now we want to get the output and print it. So double in a queue of integers, merge k sorted on our list. And then I'm going to print them out so that, so we can see what they are. So for and for printing, I need the IO stream header. That's just required. So it's IO stream. All right, double in a queue, queue algorithm IO stream. Those are our four headers. For and then print it. Add some spaces. And then print a new line at the end. So that's a lot of coding. Let's see if it compiles. We've got case 1. All right. Using cmake, and then make, and then we've got run. That's our binary. What do we got as an output? It looks like that's an increasing order. Okay, so I was correct about this direction here. Now let me show you, at this point I'm going to play around with this, and then also, oh, actually first I should cover some edge cases. So let's go ahead and separate this code out a bit for the sake of having multiple test cases and have that be easier to do quickly. All right, so run, let's say run. And it's going to take a list of lists as inputs. Take this. What that's going to do is, let's say, automatically sort them. Yeah, so we're going to sort the lists as our input, and then we're going to do all this template stuff. So this is something I can pass in, like I can call multiple times with different inputs, and it will work on all of them. Yeah, that's what I'm going for. So how will this, where I can just define this and then run it. Let me make sure that that works before we proceed too much further. Cool, that still works. All right. So we split that out since this was code that would have to be done multiple times. So we put it in its own function that owns it. And now we can just define, multiple test cases and then run them, and that's it. All right. So what happens if your comparison function's in the wrong direction? What if instead of greater we did less than? Let's see what happens. It looks like garbage. 378, 345. It looks like the two different lists concatenated, actually. So that's not totally garbage. So 3, 7, is that? So 0, 34, 78. So we got the first list over here. That looks like it's in sorted order. And then 3, 7, the second list also looks like it's in sorted order, but the two lists are in the wrong order overall because they're not combined. That's something that can happen when you've got that in the wrong direction. So one cause was this comparison operator being in the wrong direction. Now what happens if that's in the right direction, but your input is not sorted correctly? So let's go ahead and just comment that out and give it a run. Yeah, it looks pretty similar. It's just the order's all messed up. It's all garbage. Yeah, so this is one condition of this algorithm, is that the input has to be sorted correctly. Each individual input list. Otherwise, you're gonna be stuck. All right, so return. Let's restore that, and then now let's play with what happens if how do you sort it in decreasing order? So in this case, we have to have the inputs be sorted in decreasing order. So what this function is, this gives you an iterator to the quote beginning and end of the reverse order. So reverse iterator. That's what the R means. Reverse iterator. So to go from last to first, and you sort that in, quote, increasing order, which the result is you get a decreasing order output. So this is going to sort the list in decreasing order. Iterator from last to first. And then you also have to flip this sign. So those two have to be congruent. So first, let's actually show you what it looks like when they're not congruent. Yeah, we have our same kind of garbage looking output. Now when they are congruent, okay, cool. It's sorted in decreasing order. Looks like some crazy stuff. So now let's add some edge cases. Let's test it a little further now that we've got a happy path. All right, shrink that a bit. Void case 2. Let's do some edge cases. Let's do some empty input, and then something that's like, I don't know, some negative numbers. And then some duplicates. And then that's it. Let's just see how that goes. So this would be, right now, it configured to sort in decreasing order. I'm going to set it to reset it to sort in increasing order, because that's fine. That's a little more generic. So change the congruency sign, and then the sorting I want to be in regular order on the input. All right, run it. Sort in increasing order. What's missing? Oh, I didn't call the test case. Okay, try that again. -55, -44, a bunch of zeros, and it looks like it didn't hit any errors based on this. And then, so let's just let's try last thing. Let's try an empty list of lists. Is this gonna work? Is this, maybe that would mess up the constructor. Oh yeah, totally blank output. That's fine. That's okay. So the size of this list is 0. So this, let's see, initialization's gonna go from 0 to less than 0. So this is never gonna happen. And the queue is going to be empty from the start. And then same thing if we've got, we already showed, but a couple of these empty inputs, whatever. Same output. Cool. So we've got regular sorting. We had some. Let's go back to numbers with negatives and duplicates. Let's do I need duplicates from both. So there's duplicates on both inputs. We need a total of 5 zeros. 1, 2, 3, 4, 5. That's 5 zeros. Cool. This looks pretty robust. So the main case is talked about time and space complexity. We talked about some of these edge test cases, meaning, blank inputs, missing inputs, duplicates. Does it handle as the size of the outputs of 1, 2, 3, and then 5 zeros? That's a total of 8. 1, 2, 3, 4, 5, 6, 7, 8 items. Nothing's getting lost. So, all right, so as a recap, we've got 3 headers, double in a queue, a priority queue, and an algorithm for sorting. These second 2 headers are just for testing purposes. They're not for the actual main function. Custom comparison function, where if you want to go in increasing order of your sorting, you want the first item to be greater than. So it's true. If it returns true, then that assumes A is smaller. So A should come first. Wait, no, that's backwards. Priority queues by default. I guess that means, you know what, let's pull up in documentation. And this is generally legal for a problem like this, but you should definitely ask your interviewer first. They'll most likely give you the go ahead. Just make sure you read the documentation thoroughly. So C++ priority. So for example, I have been allowed to look up the syntax for lambda expressions. Container provides constant time lookup of the largest, so default largest of the element at the expense of logarithmic insert and extraction. So yep, that's what I said about logarithmic operations. But you get constant time lookup of the, in this case, largest by default. So if we want to go in increasing order, we want to lie. So by default, it's gonna this would be default behavior. So it returns true for whichever of the smaller ones, I guess. So it's like the opposite of what you think. In order to go in largest by default, then that means that if A is smaller, then it's going to put that last. So this returns true for which item would come last in the queue. So if you want A to come last, then you return true when it's smaller. And if you want B to come last, then you return true when it's smaller. So if you flip the sign, you get the opposite behavior. That's what we were looking for. It is greater by default. So this returns, yeah, that the ordering is flipped from what you might see in other languages. For example, Python, that one always, you can't change that. You can't add a custom comparison function, and it always puts the smallest thing first. This is the opposite for C++. Checking edge cases for empty inputs here, do that in a couple of places. And we are funneling the different lists through this priority queue and getting out one single line like a sausage maker. And that's the algorithm. I'm going to go ahead and cut that there. This has been long enough. You folks are very, very patient. And good luck on whatever it is you're preparing for.